So on to statistics. This is the statistical hypothesis testing, chapter 22, mixed exercise, looking at question 5, which says that I have a doctor who knows that 20% of people suffer from side effects when treated with a certain drug. He wants to know if the proportion of people suffering from side effects is lower with a new drug. Immediately I have a clue. Let's break a sec and say that lower is telling me I'm going to perform a one-sided test. It's not asking for a change, in which case I would suggest there'd be a change either up or down, but it's very much saying lower, so it's a one-sided test, which will matter when I talk about significance in a moment. We carry on. He looks at a random sample of 30 people treated with the new drug. So when I look at my binomial distribution, I'm going to have 30 possible tests to complete. What's the largest number of people who could suffer from side effects and still lead to the conclusion at the 5% significance that the new drug has a lower proportion of side effects? And I'm given options 2, 3, 4, or 5. Well, let's make some assumptions. Let's assume that the rate of side effects follows a binomial distribution, x and p, as we're used to. And we know that generally that proportion is 20%, which is 0.2 when I come to put it into a calculator. And we're told that I have a test of 30 samples. Indeed, why am I putting an X there? I'm so sorry. That should be an N. Of 30 samples, so that's going to be my N value. And I'm going to get some number out of there. Now let's see what happens. When I have my my graph, it'll look something like that, the frequency of each value, and I'd expect that point there to be at 6, because 30 times 0.2 is 6. And there's some lower chance of getting 5, some lower chance of getting 4, some lower chance of getting 3, and down to 2. And at some point, I would expect that there's a sufficiently small area of this graph that one of these numbers represents that I can say at the significance level of 5%, I am convinced that there is enough evidence to suggest that there is a lower rate of side effects in the alternative drug. So let's see what happens when I do that. So I go to my calculator and I go to number 7, which is my statistics bit, and say I go to my binomial CD. I'm looking for a variable, and let's see what happens with each of these x values. Well, let's start with an x of 6 just to see what happens. My n value will have 30 samples and my probability is 0.2. I put those values in and I get 0.6. Let's put these values in. There's my x, and this is my p that I get out. And when x is 6, I get 0.61 or so. When I come to say, let's say that's 5, so I'm only looking at this area from here back here, I get 42%. So that was 5, that's 0.43 in fact. Next one, let's make that 4, and I get 25%. So if I only wanted at a 25% significance level, which is very, very high, I'd have to get around 4 people. Let's see what happens if I make it 3. I'm down to 12 and a bit percent now, 0.12. And then finally, let's look at 2, and we'll interpret these in a second. If it's 2, I get down to 0.04. 0.44. Sorry, it's off screen. So what's that telling me? That's telling me that the proportion of the total area under this curve, which of course sums to 1, the proportion left of each of these values at 6 is 61%, at 5 is 43%, at 4 is 25%, at 3 is 12%, and at 2 is, well, 4 and a bit percent. So at the 5% significance level, I'm saying I'm allowing up to, well, about there really. And so 2 is the highest number of people I would expect, or I would allow, for me to suggest that the alternative drug has a significantly lower proportion of side effects. And that's an important phrase, significantly lower. And that's how we do it, using the calculator and using these numbers to go into a binomial distribution.